Okay, so need to start today by going back to this question D yesterday. I knew there was something not quite right with that, and I learned something new yesterday because we checked this graphically. But here's what I did do wrong, and I remembered this when I went back and looked at it after, and I talked to Miss Calvert about it as well, is that you cannot use the power law here. And the reason for that is you're eliminating the square on the x plus 3. The argument, because it's x plus 3 squared, has to be a quadratic. And when you use the power law here, you're taking away that squared on the x plus 3, which makes it a quadratic, no longer a quadratic term, but a linear term. So because of that, you cannot do this step that I did yesterday. So we're going to fix that one. And also, because this quadratic is still there, the restriction is not that x must be greater than negative 3. We only have one restriction here, and that is that x cannot equal negative 3. Because the argument has to stay x plus 3 squared, that means no matter what you get inside the bracket, you're going to square it anyways. So if you get a negative inside the bracket, let's say when x is negative 5, it doesn't matter because you're going to square. Negative 5 plus 3 is negative 2. When you square it, you'll get positive 4. So you'll never be taking the argument, or the argument will never be negative here. But there is still a non-permissive value of negative 3. So we would say that here, that x plus 3 cannot equal 0. So x cannot equal negative 3. That is the only non-permissive value. So to solve this, to do it properly, I would convert from logarithmic to exponential. I would start with the base and cycle through, which will give us 2 to the power 4 equaling x plus 3 squared. And again, you have to keep that squared there because the argument is a quadratic. So 2 to the 4th, which is 16, will equal, when you square this binomial, you'll get x squared plus 6x plus 9. And then you subtract the 16 from both sides to make the quadratic equal to 0. 9 take away 16 is minus 7. And then this quadratic is factored. X plus 7, x minus 1 equals 0. And that gives us two different sets of solution. Remember, they occur when each factor equals 0, which gives us negative 7 and positive 1. Now again, our only restriction here is that x cannot equal negative 3. So that does not eliminate any of our solutions. So here's what I learned yesterday. And I didn't realize this before, after all these years using this calculator. When you put log base 2 of x plus 3 squared in the calculator, just like it's written, what that really means, it means all of the log base 2 of x plus 3, all of it squared. When you put it in the calculator like this, which I'll do now, so log base 2 of x plus 3, all squared, when you put that in there, what the calculator thinks, it thinks that all of it is squared. The log base 2 is also squared as well as the x plus 3, which is not what this is saying. This is saying only the x plus 3 is squared. But when you put it in like that, your calculator thinks it's all squared, which is what I did yesterday when we checked it on the graphing calculator. So when we did it, this is what we got. And we got an answer of negative 2.75 over here, which when you checked it, it didn't work. But that is the wrong graph. We put it in exactly the way it's written on the page, but it's the way the calculator interprets it. And I didn't know this until I talked to Miss Calvert yesterday. So you cannot do this one graphically unless, and I think if you change this and add an extra set of brackets in there, insert and insert brackets there, and then that's where the squared appears. So we'll eliminate this square there. So I think this will work. Yes, it does. Okay, so when we check these, there's our positive 1 answer. If I put my guess at -7, there it is there. So they both work according to the graph. Okay, now the other thing we could do is we could check them algebraically. So let's check these algebraically. Let me just move these over a little bit so we have a bit more room. So let's check these algebraically. So the original expression is log base 2 of x plus 3 all squared must equal 4. So first, let's check for -7. This will be log base 2 of -7 plus 3 all squared. -7 plus 3 is -4, but -4 squared is 16, and log base 2 of 16 does equal 4. That's asking 2 to what power is 16. So -7 does work. And when we check for positive 1, it'll be log base 2 of 1 plus 3 all squared, which is log base 2 of 4 squared, which again is 16, and that is 4. So they both check. They both work. So again, the way I did this before yesterday is wrong, and it's funny because when I looked in my key, I didn't change it to the power law, but as I was looking at it, I was thinking, well, why won't this work? But it doesn't work because you're eliminating the fact that the x plus 3 needs to be squared, so the argument is a quadratic, which is how I had it in my key, but I just thought I could do maybe a different way. The other, well, it's not really a mistake, it's just that I didn't realize when you put this expression into the calculator exactly as it's written, it thinks that the log base 2 of x plus 3, all of it is squared. The log base 2 as well as the x plus 3, when that's not correct. Only the x plus 3 is squared. And so this is how it must look in the calculator to do that. So that was something new for me. Okay, so I guess the thing to remember is because the argument, the x plus 3 is squared, that means the argument is a quadratic, so it has to stay a quadratic. Okay, so let's go on to the next page. So this says use or solve, and round answers to 2 decimal places. We're solving exponential equations using logarithms. So this is one of the more, I guess, popular uses of logarithms. Back in chapter 7, we solved exponential equations, and we solved them by making the bases the same. And I said at that time, when you have an exponential equation where you can't make the bases the same, you can use logarithms to do that. And so that's what we're going to do, right? We saw that you could solve these on a graphing calculator, but the only issue with that is it gave us answers that were irrational in many cases. So you had to round them. They're no longer exact. If you want exact values, then you would use logarithms. Now, it does say solve and then round your answers to 2 decimal places, so that's fine. But we are going to use logarithms to get the answers as exact values first, and then we can write them as decimals rounded to 2 decimal places. So there's a couple different ways you can do these, and I'll show you both ways. One of them would be to take the log of both sides. That's one possible way you could do this. So we'll say this is solution number 1. Take the log of both sides. So the log of 4 to the x must equal the log of 605. So this is just doing the same thing to both sides of an equation. Normally we add values to both sides, we subtract values, we multiply, we divide, square, square root, we've done all that. But you can also take the log of both sides. And then on the left side, you can use the power law. X log of 4 equals log of 605. And then to get x by itself, you would just divide both sides by the log of 4. And x would equal log of 605 over log of 4. And these are both common logs, which is base 10. So we can use the log key to evaluate these. So the log of 605 divided by the log of 4. So there is your answer as a decimal, which we will round to 2 decimal places, 4.62. But the expression above is the answer as an exact value. Log 605 divided by log 4 is the answer as an exact value. So that is one way to do this question. Take the log of both sides, use the power law, solve for x. The second way, which we'll call solution 2, is taking the expression and converting from exponential to logarithmic. We have 4 to the power x equaling 605. That's an exponential function. If we convert to logarithm by starting with the base and cycling through, remember the base in either form is the same. The exponential has a base 4, so the log will have a base 4. If we start with the base and cycle through, the next thing you write is 605 equals, the last thing you write is the x. Start with the base and cycle through. So you're left with log base 4 of 605 equals x. And log base 4 of 605, if you use the change of base identity, is log 605 over log 4. So it's the same thing. We're going to get the same answer. So if you have the newer operating system, you can put it directly in, which we have been doing, log base 4 of 605. So you get exactly the same answer. This, what we have written down there, is the exact value. You use the calculator to get it as a decimal, which you round to 2 decimal places, get the same answer. Now the second way is a little bit quicker. You can see there's a fewer steps there. Okay. A fewer steps. So that is a little bit quicker. So if we're going to do that going forward, you must get the exponential part by itself. So for question B, you would start by dividing both sides by 8 first. And that will leave us with 3 to the 2x equaling on the left. On the right side, 568 divided by 8 is 71. And then we will convert from exponential to logarithmic. We'll start with the base and cycle through. Remember, the base in either form is the same. The exponential function has a base of 3, so the log will have a base of 3. The cycling through tells you the order the other pieces are written in. So after the base 3 comes a 71. After that comes the 2x. And then if you divide both sides by 2, you'll have x by itself. So x as an exact value is log base 3 of 71 divided by 2, which is the same as multiplying by a half. Either way, it's the same thing. So if we go to our calculator, 1/2 or 0.5 times log base 3 of 71. So what we have written down on our page right now is the exact value. We can use our calculator to get as a decimal, which we have to round. We're told to 2 decimal places, approximately 1.94. the 2 decimal places. If you wanted to do it the first method, which is taking the log of both sides, once again, I would divide both sides by 8 first. And then you could take the log of both sides, use the power law. You will get the same expression in the end. They both work. So even though for question C, both sides are exponential functions, you can still convert from exponential to logarithmic. We'll start with the base on the left and we'll cycle through. So again, when you do that, that tells you the order that the other pieces are written in. The base on either form is the same. We're starting with the expression on the left with the base of 4. That is the base of our log. After the base 4 comes 3 to the x plus 2 equals, on the right side, you'll have 2x minus 1. So that's what it'll look like when you convert from exponential to logarithmic. So the expression on the left is a log. We can use the power law to bring the exponent in front as a coefficient. The power of x plus 2 comes in front to make a coefficient. And remember, we're trying to solve the equation. We want to know what x equals. That's the whole point. So we need to solve for x. So what I would do on the left is I would multiply out the brackets. Both terms inside the bracket is multiplied by the log base 4 of 3. The x is multiplied by the log base 4 of 3, as well as the positive 2. Because remember, we want to solve for x. We want to know what x equals. So I multiplied out the brackets, both terms inside the bracket, multiplied by the log base 4 of 3. I know I need to get x by itself, so I'm going to collect all the terms with x on the left side. Whoops. I don't know why I wrote x there. That should have been a 3. So again, I'm going to collect all the terms with x on the left side, which is x log base 4 of 3. I'll subtract the 2x from both sides. It'll become a minus 2x on the left. On the right, I've got a negative 1, and I'm also going to bring the 2 log base 4 of 3 to the right by subtracting it from both sides. So remember, I want to solve for x. I need to get x by itself. So on the left, I'll take out a common factor of x. And then we would divide both sides by what's inside the bracket to get x by itself. We would divide both sides by log base 4 of 3, take away 2. That is a factor. You can divide both sides by the same factor so that they cancel on the left and you do have x by itself. So there's the exact value. You could simplify it a little bit by using the power law for that second term on top. The coefficient of 2 could come up as an exponent that becomes 3 squared, which is 9. So there's the exact value for x. To get it as a decimal, I would have to use brackets to keep the numerator and denominator together. Negative 1 take away log base 4 of 9. So close the bracket to keep the numerator together. All divided by, in brackets, log base 4 of 3. Minus 2. Close the bracket. So if we round to the nearest hundredth, it'll be approximately 2.14. Okay? You could also do this by taking the log of both sides and then move the exponents in front as coefficients. The exact value expression will look different. It'll look a little bit different, the exact value expression, but it'll have the same value at the end when you work it out. Okay? You can always check any of these by graphing them. So you should never get these wrong. You can check any of them, either algebraically or graphically. Usually the algebraic check is a little difficult only because your answer will involve a log. Okay? But it could be done. It can also be done graphically. So if I want to check C graphically, my first equation will be the left side, 4 to the power 2x minus 1. The second equation will be the right side, 3 to the power x plus 2. So just check both those, 4 to the 2x minus 1, 3 to the x plus 2. Zoom 6 to set our windows to their standard settings. If we find our point of intersection, second function trace, number 5 for intersect, enter, enter, enter. There we get 2.14. Even though you can't see it on the screen, you can see the y value is 94.5. Because the x windows do contain the solution, the calculator will do it. If the x windows between -10 and +10 didn't contain the solution, you'd get an error. You'd have to expand your windows. But because the windows do contain the solution of x, even though you can't see it, it does still give you the answer. And if we compare that to the answer we got algebraically, that's the last x value we have in our calculator. So when I go x enter, it spits it out. It's exactly the same. So it checks. You should never get these wrong, or at least you should know that the answer you get is not correct, because you can always check them graphically. Okay? Right, so some more questions. Same thing. And I will do these all the same way. I will convert from exponential to logarithmic by starting with the base and cycling through. Remember that the base in either form is the same. When you do that, you get your answer in one step. When you start with the base and cycle through, you get the answer in one step. The answer is, as an exact value, will be log base 2 of 2500. Which is approximately 11.29. If you don't have the newer operating system, you must use the change of base identity. That would be the log of 2500 in brackets divided by the log of 2. Same answer. And it could be checked algebraically. 2 to the x will be the first equation. Y equaling 2500 will be the second. When you graph it, you won't see that second equation because it's y equals 2500. Right now, my maximum value is only 10. So you could make your y max higher than 2500, so you could see it. If you try and find the solution right now, you'll get an error because the window, the x max is at +10. It does not include my solution of 11.29. So we're going to have to change our windows here anyway. So let's make our x max 12 and change our scale to 2. Let's make our y max 2600 and let's change our scale to, let's say, 500. Now when we graph it, we should see the solution and we can find it. So the answer is 11.287712, which rounds to 11.29. If I go back and get my x value and compare it to what I found when I calculated it, It's exactly the same decimal. Okay. So the next one, again, I will do this by converting from exponential to logarithmic. It'll be log base 5 of 1700 equals x minus 3. And then to get x by itself, you would just add the 3 to both sides. So it'll be log base 5 of 1700 plus 3. There's the answer as an exact value. We can use our calculator to get it as a decimal. Log base 5 of 1700 plus 3 has to be outside the bracket. So if we round it, it's approximately 7.62. Again, this is one of the most frequent uses of logarithms. You can solve any exponential equation using logarithms. Back in chapter 7, when we did it, we had to get the bases the same. In these cases, you can't make the bases the same, which is why the answers are irrational. So again, you could check that on the graphing calculator, but let's do question C. We'll check this one. And again, we'll start with the expression on the left with a base of 6. We'll start with the base and cycle through. This tells us the order the other pieces are written in. Remember, the bases are the same no matter which form you're writing it in. The exponential function on the left has a base of 6. That is the base of our log. After that comes our 8 to the x plus 3. After that becomes the 3x plus 1. So if you convert to logarithmic, that's what you get. So on the left, we would use the power law. Bring the coefficient, bring the power in front as a coefficient. You're going to multiply the log base 6 of 8 by both terms in the brackets. The log base 6 of 8 is multiplied by the x as well as by the plus 3. And because we want to solve for x, we want to get x by itself. Are you with us, Blanny? We're going to collect all the x's on the left. So I'll keep the x log 8, log base 6 of 8 on the left. I will subtract the 3x from both sides. I'll keep the positive 1 on the right, and I'll subtract the 3 log base 6, 8. Log base 6 of 8. Subtract it from both sides to move it over. So now we have terms involving x on the left. We have terms that don't have the x on the right. Take out a common factor of x on the left. And then we would divide both sides by what's inside the bracket to get the x by itself. So that those cancel. So what we have on the right is the exact value. Now, you cannot cancel log base 6 of 8 from the top and the bottom there. You cannot, because those are terms of binomials. You can only cancel factors. You cannot cancel terms. So you can't do that. So that is the answer. You can simplify it a little bit because that second term on top, you can use the power law to bring the coefficient of 3 up as an exponent. 8 to the power 3 is 512. So you could write this as 1 minus log base 6 of 512 if you wanted to, over log base 6 of 8 take away 3. So there's our answer as an exact value. If we want to write it as a decimal, which it does ask us to do to 2 decimal places, we can put this in our calculator. 1 minus log base 6 of 512 in brackets, all divided by, in brackets, log base 6 of 8, take away 3. So that's approximately 1.35. Let me put that in the calculator. And we can use the calculator to check this. Equation 1 will be the left side, 6 to the power 3x plus 1. Equation 2 will be the right side, x to the power, 8 to the power x plus 3. Zoom 6 to set our windows to the standard settings. And our answer should be at 1.35. And even though we can't see that, that number is within the windows that we have, our x windows, so the calculator will give it to us. Second function trace, number 5 for intersect, enter, enter, enter. And we get x equaling something that rounds to 1.35. If I quit out of there and go x enter to retrieve that last value of x from our graph, we see that it is exactly the same decimal that we got. So you can always check these on the calculator. Okay, so let's look at some questions involving logarithmic equations. Paleontologists can estimate the size of a dinosaur from incomplete skeletal remains. For a carnivorous dinosaur, the relationship between the length, S in meters of the skull, and the body mass, M in kilograms, can be expressed using a logarithmic equation. 3.6022 log S. So remember, S is the length of the skull, and that equals log M minus 3.4444, where M is the body mass in kilograms. S is the length of the skull in meters. Determine the body mass, so you want to know what M is of a dinosaur, an Albertosaurus dinosaur with a skull length of 0.78. So there's the equation that we're going to use. 3.6022 log S equals log M minus 3.4444. So in this case, you're given a skull length of 0.78. That's S. And that equals log of M minus 3.4444. So let's move this down so we can see it better. Okay, so we can calculate what the left side of this equation is, because that log is a common log by going 3.6022 times the log of 0.78. So the left side is a decimal, negative 0.3887. Let's round that to. negative 0.3887. Yeah, so we rounded it, but we're going to keep this number in our calculator as we go along. We need to solve for m. That'll give us the body mass of that dinosaur, which our next step would be to add the 3.4444 to both sides. So I'll get rid of those on the right side. And we'll be left with log m on the right equaling what we get when we add those together. So we'll add 3.4444 to that previous answer, which gives us 3.056. And again, I rounded it to write it down, but I'm going to keep that number in our calculator. And now to find out what m is, we would convert from logarithmic to exponential. That log on the right is a common log, which means base 10. So if I start with the base and cycle through, it'll be 10 to the power 3.056, which again is a number that I rounded, but it's in my calculator. That's what m will equal. So I'll go 10 to the power of the previous answer. So that gives us 1136.85. Does it ask us to round to the nearest kilogram? So that would be 1137 kilograms. So that would be the body mass of that dinosaur if its skull length is 0.78 of a meter. All right. So part B, in this case, you want to find the skull length if the body mass is 5,500 kilograms. So again, the formula is 3.6022 times log S. S stands for the length of the skull, which we're trying to find. And that equals the log of M, the body mass of this dinosaur is 5,500 kilograms, minus 3.4444. So in this case, we can get the expression for the right side by using our calculator. Again, these are common logs. So we can just use the log button. Which gives us that irrational number on the right, 0.29596. So we'll say 0.296. Again, I rounded it to write it down, but we'll keep that number in our calculator. Our next step would be to divide both sides by the 3.6022. That'll get the log of S by itself. And I've got that decimal in my calculator, that 0.296. We keep it in there and divide by the 3.6022, which gives us log of S equaling approximately 0.082. And then I would solve for S by again converting from logarithmic to exponential. That log on the left is a common log base 10, and we start with the base and cycle through. It'll be 10 to the power 0.82, 0.082 I should say. Equaling S. So I've got that decimal in my calculator. I want to keep it there. 10 to the power of the previous answer. It does say to the nearest hundredth of a meter, so it'll be 1.21. meters when we round to the nearest hundredth. Okay? When an animal dies, the amount of radioactive carbon-14 in its bones decreases. Archaeologists use this fact to determine the age of a fossil based on the amount of carbon-14 remaining. The half-life of carbon-14 is 5,730 years. So that's how long it takes for half of the original amount to decay. Head smashed in Buffalo Jump in southwestern Alberta is recognized as the best example of a buffalo jump in North America. So you can go there. It's a historic site. It's south of Calgary. And so the First Nations people, they used to chase a herd of buffalo towards this cliff, and the buffalo would run off the cliff. And they would hit the bottom and they would die because of how high it was. And then the First Nations people would go down there and they'd harvest the meat. So they did this, and they didn't have to shoot the buffalo with their whatever they were using. They just had to chase them off the cliff. And so you can go there. It's a historic site. So the oldest bones unearthed at that site had 49.5% of the carbon-14 left. How old were the bones when they were found? So to do these, we use the exponential function equation that you're given on the formula sheet. And that is y equals a times b to the power t over p, where y is the final amount, a is the initial amount, b is the growth factor, t is the time, p is the growth period. So we'll write all that out. So y will be our final amount. A is the initial amount. B is the growth rate. T is the time. And P is the growth period. So you're given this equation on the formula sheet, but you're not given what each of those parameters represents. So that's something that you would need to know. All right, so y is the amount at the end. It says that the oldest bones that were unearthed had 49.5% of the original carbon-14 left. So y, the final amount, is 0.495 times the initial amount, which is A. A is the initial amount, which in this case, because we're not given how much carbon-14 was there to start with, we leave it as A. The amount at the end is 49.5% of what they started with. 49.5% of A. And you remember that whenever you're working with a percent, you change it to a decimal. Percent means a number out of 100. So 49.5% means 49.5 out of 100, which gives you your 0.495. So B is our growth rate, which in this case is a half, because the amount of carbon-14 is being cut in half every 5,730 years. We want to know how old the bones were, so we want to know what T is. Our growth period is 5,730 years, because that is how long it takes for the amount of carbon-14 to be cut in half. We need to solve for T, and T is always the same unit as P. Our T will be years. So we need to solve for T. In this case, we can divide both sides by A. We have a factor of A on both sides. We can divide both sides by A, and they will cancel on the right and the left. So we're left with 0.495 on the right equals 1/2 to the power t over 5730 on the right. And we need to solve for t. We need to solve this exponential equation. And we can do that by converting from exponential to logarithmic. Right? The exponential function on the right has a base of 1/2. We'll start with the base and cycle through, and that'll tell us what order the other pieces are written in. But you start with a base of 1/2. That is the base of the log. After the base of 1/2 comes a 0.495, and after that becomes t over 5730. Before we solve for t, we know that the answer is going to have to be something a little bit higher than 5730. It takes 5730 years for half of it to decay, for the amount left to be 50% of what you started with. Our amount remaining is a little bit less than 50%. It's 49.5%. So the time will have to be something a little bit greater than 5730. Okay? But let's get that answer by multiplying both sides by 5730. To get t by itself, you'd multiply both sides by 5730, which means you'll have 5730 times log base 1/2 of 0.495. So we'll find our answer by using the calculator. 5730 times log base 1/2, which we can write as 0.5 because it's exactly 0.5 of 0.495. And our answer is approximately 5,813 years. Right? The unit for t is the same as the unit for p, which years. And like we said, the answer would have to be something slightly greater than 5,730 years. Okay? So on the next page, we're actually given the equation. The rate at which an organism duplicates is called its doubling period. That's why the base is 2 for this equation, because that is the growth factor, the growth rate, I should say. Okay? It's doubling, so the base is 2. The general equation, n at t equals n sub 0 times 2 to the t over d. So this follows the same pattern as our exponential function equation. N is a number present after time t, so the final amount is n at t. N sub 0 is the original amount. T is the time, and d in this case is our growth period or our doubling period. How long it takes for the organism to double, the number of cells to double. So E. coli is a rod-shaped bacterium commonly found in the intestinal tract of warm-blooded animals. Some strains of E. coli can cause serious food poisoning in humans. Suppose a biologist originally estimated the number of E. coli bacteria in a culture to be 1,000, and after 90 minutes, the estimated count was 19,500. What is the doubling period? So we want to solve for P to the nearest minute. And it's in minutes because our time is minutes. The time that has elapsed is 90 minutes. So n at t is the number at the end, which is 19,500. And that'll equal n sub 0, the original amount, which is 1,000, times 2 to the power. T, the time elapsed, is 90 minutes. We want to find out what d, the doubling period, is. So we need to solve for d. I would start by dividing 1,000 on both sides. That'll give the exponential function on the right by itself. On the left, when you divide by 1,000, you move the decimal 3 spots to the left because there's 3 zeros. That'll give us 19.5 on the left, equals 2 to the power 90 over d. And we will solve this by converting from exponential to logarithmic. We'll start with the base and cycle through. The bases are the same, so it'll be log base 2. As you cycle through, it tells you the order the other pieces are written in. Log base 2 of 19.5 will equal 90 over d. And we need to solve for d. So I would multiply both sides by d, and then divide both sides by the log to get d by itself. So our answer will be found by going 90 divided by log base 2 of 19.5. 90 divided by, if you're using the log function in the calculator, if you have it, you can just put it in there. Whoops, 19.5. So to the nearest minute, that's approximately 21 minutes. That is the doubling period. That's how long it takes the number of cells to double. If you don't have the newer operating system and you need to use a change of base identity, it would be 90 divided by, you'd have to go log of 19.5 over log 2. So you're dividing by a fraction, which means you could multiply by the reciprocal. You could put it in your calculator that way. You'd only have to do this if you didn't have the newer operating system, if you didn't have that log function where you can put any log with any base in there. So it'll be 90 times the log of 2, close the bracket after the 2, divided by the log of 19.5. It gives you exactly the same answer. And you wouldn't necessarily have to do that step of multiplying by the reciprocal. If you use brackets, you could go 90 divided by, then you'd have to use brackets to keep all that log part together. You get the same answer. Okay? So, what I'd like you to do for practice is on page 412 to 414. We're going to do questions 1 and 2 on 412, 9 through 14 on the other pages. We should be able to finish this chapter off tomorrow, which means you're going to have a quiz on Thursday on chapter 8. I'll also be handing out your review assignment for you to work on over the long weekend. You'll get that tomorrow because you'll be writing your chapter 7 and 8 unit 3 exam on Monday. Okay? So, assuming we can get through everything else tomorrow, which we should be able to, that'll be the plan. Okay? So tomorrow it'll just be some more examples using that exponential function equation to solve problems.